Okay, so I said there was three main things that we really want to know about the Yoneda lemma to use it. And the first thing we've just covered, which is the most essential thing, the nature of this kind of isomorphism, which the Yoneda lemma is about. Now, the other things are basically about how we can use the Yoneda lemma. So the idea is that if we have a kind of E element theta of x, then we can kind of equivalently think of that as an arrow, theta under arrow, from hom E comma blank to x. Okay, so it's this idea of kind of representing stuff inside x as arrows into x from hom functors. Now, in order to be able to do that, we really want two other results, and I call these the action lemma and the natural lemma. So the action lemma is basically about how if we have an E element of x, in other words, if we have an element theta of this set x of E, well, we might want to do an S action on that theta. And when I say that, I mean we might want to compute x of S of theta. So this is just another piece of sort of terminology. We might want to refer to this as the results. So we could call this the results of doing an S action on theta. Okay, so basically this is just some kind of verbal shorthand for saying that we kind of take this arrow S from E to V, which is an arrow of the category C. We lift it under this functor X, so then we have this functor X of S, which is a really, for us, it's a function from X of E to X of V, and then we perform that function on this element theta of X of E. So we call the result then the result of doing the kind of S action on theta. So in our kind of example, this sort of thing would really correspond to, for example, finding the vertex of a loop. Okay, if we're dealing in this category of functions. So if we have a bouquet, it has a load of loops. If we're thinking of a particular loop, theta, that would really be an element of X of E. And then if we want to find out what the vertex of that loop is, we'd be doing X of S on that theta. Okay. And what I'm saying is that that's a sort of element-centric way of looking at things, but there's also this kind of Yoneda-based or arrow-centric way of looking at things, and that's what the action lemma tells us about. Now, that's one thing, is this action lemma. The other result we want to talk about is called the natural lemma, and that's about how we can think about doing kind of arrows, because I mean arrows in our category set to the power of C, they're really like natural transformations between functors, and we can think about how E elements get moved around by those kind of arrows, those kind of natural transformations, and the natural lemma tells us how to think about that in terms of this kind of arrow-centric Yoneda-based kind of viewpoint. So this action lemma and the up-and-coming natural lemma are really results of my own invention, but they kind of easily fall out of the kind of naturality of this isomorphism behind the Yoneda lemma. It's just that there's quite a lot of details, to like prove that the Yoneda lemma is like the isomorphism involved in that is a natural isomorphism and so on. And I didn't want to go into too many details, so I'm just going to sort of extract out the salient results, which I call the action lemma and later the natural lemma. So anyway, what is this action lemma? Well, basically, it's easiest just to show you in a picture, to be honest. So this is a picture of what the kind of action lemma means for us when we're looking at this category of functions. Okay, so in this case, of course, we're looking at this category set to the power of a category with an arrow like this, and then an object in that category. In other words, an object in this category of functions. We can visualize it as a bouquet. So we can think of X as a bouquet here. And the idea is that if we have an E element of X, in other words, if we have a loop, let's say we call it theta. So we have this theta, which is an element of X of E. Well, let's say we want to do the S action on that theta. Okay, so we can do this. Remember the category which this all comes from basically looks like this. There's an arrow X from E to V. And we can do the kind of S action on theta. And, you know, this is the result here. X of S of theta. Okay, so this is the result of doing the S action on theta. And you see it's fairly simple graphically. We just have a loop, and the loop is called theta, and X of S of theta is just the vertex of that loop. But this is all really kind of element-centric ways of looking at things. And the action lemma tells us how we can think about this in a kind of arrow-based way. So the basic idea is that using the kind of Yoneda correspondence for this E element of X, this theta here, we can find a kind of corresponding arrow, theta under arrow, which is really a natural transformation from Hom E comma blank to X, as indicated by these blue arrows here. And the idea then is that, yeah, this represents theta, but what kind of arrow into X represents the vertex of theta? Well, to get that, we just do theta under arrow after H S, okay? And that composition is going to give us an arrow from Hom V comma blank into X. And it turns out that that composition is equal to X of S of theta under arrow. In other words, the composition of this blue arrow and this green arrow is this arrow which is kind of representing this vertex, which is the vertex that theta is a loop of. Okay, so this is the idea. So to say it formally then, the action lemma, which, you know, holds in general for a category of functors from C to set for any category C, well, at least any small category. Well, the lemma says that for theta in X of E, for an arrow S from E to V, we have the X of S of theta under arrow is equal to theta under arrow after HS. Okay, so I think I've explained what this means with the picture, so let's have a look at the proof. So to prove this, basically we have a natural transformation here and a natural transformation here, and we want to show that they're equal. So we'll just pick an arbitrary component. So we'll look at the W component of these natural transformations, and that's just going to be a function. So it's going to be a function from Hom V comma W to X of W, and we want to show that those two functions are equal. So we're just going to show that those functions work the same way if we think about how they're working on an arbitrary element X of Hom V comma W. Okay, so more formally then, let's let W be an object of C, and we'll let X denote an arrow from V to W. And then we're going to think about how the W component of theta under arrow after HS works on a sort of arbitrary element X of HOM V comma W. And so this green arrow here, what we're trying to do is we want to show that this green arrow works the same way on X as does this orange arrow here, which is X of S of theta under arrow, well, the W component of that, okay? Because basically what we're doing with this green arrow and this orange arrow is we've just isolated the W component of these natural transformations, which we're trying to show are equal here. So we want to show that the green arrow and the orange arrow do the same thing to this sort of arbitrary element X of HOM V comma W. So all we have to really do is compute the results and show that we get the same result in each case. So firstly, let's deal with this green arrow. So this is theta underlined after HS, and we're looking at the W component of that. And we want to perform this function on this element X of HOM V comma W. So, well, we can break this into two steps, okay, because we can write this as theta under arrow, the W component of that, after the W component of HS, okay. So we break it into these two steps, as I'm showing in with the purple arrows. And one important question then is, well, okay, let's do it in steps. So firstly, what happens to X when we do the W component of HS on X? Well, let's just recall how HS works. So we have it up here, look, the W component of HS is going to send an element X to an element X after S, okay? So this sends X to X after S. And then we need to do the second leg of this. So we then want to understand what the W component of theta under arrow does to X after S, okay? So we need to remember now how theta under arrow works. And this is the kind of formula I've already showed you, is that the V component of theta under arrow sends S to X of S of theta. This is kind of comes from the main sort of definition of the kind of arrow from the HOM functor that corresponds with theta under this kind of Yoneda correspondence. But this is really a formula that's working for an arrow S from E to V in our category C. But in our case, we're really more interested in this. We want to do the W component of theta under arrow on XS, okay? But we can just use a similar formula because, you know, the same kind of formula arises. It's just now we've got this arrow XS, which is an arrow from E to W. And so the results of doing the W component of theta under arrow on XS is just going to be capital X of XS of theta. Okay, so that's the result that we get. So this is the result then, shown at the right, of doing this green arrow, starting from this element little x of HOM V comma W. So now all we need to do is work out what happens when we do the orange arrow on this little x, and we want to show that we get the same thing. So again, I rewrite this sort of formula here, which basically tells us what the natural transformation corresponding to theta looks like, but I'm just using a bit different symbols now. So what I'm saying here is that, I suppose in this case, we have instead of a theta in x of e, suppose we have some element phi of x of v. Okay, well, very similar formula will hold, of course, but in this case here, we're really applying this function here, this component of this natural transformation to S, which was an element of Hom E comma V. But in this case here, we're applying this function here, this W component of phi under arrow, we're applying that to X, which is going to be an element of Hom V comma W. Okay, but basically what we do is just the same. It's just we're using different symbols and things are a little bit different in the sort of variables that we're playing around with. But basically the result of doing the W component of phi under arrow on X is going to be capital X of little x of phi in a similar way to as I've circled in red up here. So all we do now is we just apply this formula here when phi is equal to x of s of theta. And the reason we're doing this is because we want to work out what this orange arrow here does to x. Okay, so the thing that we're operating on is indeed this element x of Hom v comma w, and the kind of natural transformation we're getting is the natural transformation corresponding to x of s of theta, and we want to do the w component of that on little x. So basically I'm saying we want to compute this result here, shown in purple, when phi is equal to x of s of theta. Okay, so we just substitute in this expression for phi here into this purple equation here, and we get that the result of doing x of s of theta, and what we get is that if we do the w component of the natural transformation corresponding to x of s of theta on x, then the result is going to be capital X of little x operating on capital X of s of theta. Okay, but we can rewrite that. I mean, that's just the composition really of x of little x after x of s operating on theta. And because capital X is a functor, we can rewrite this as capital X of little x after s operating on theta. And so this is really the result of doing that orange arrow I showed above on theta, and notice that we're getting exactly the same results as what we got when we did the green arrow on theta. So that shows that basically the green arrow is equal to the orange arrow because these two functions work just the same way on an arbitrary member of their source set. And since this works for an arbitrary component W of these natural transformations, that shows that these natural transformations are the same. And therefore we've proved this action lemma. So like this is a very important result because it basically says that when we want to do an S action on an E-type element theta, we can just get the arrow corresponding to that theta and do that after HS. Okay, and again we see a nice picture of what this looks like in this kind of category of functions here. So we have this bouquet corresponding to X. We have this E-type element theta of X. And we have this kind of arrow, theta under arrow, corresponding to theta. And then if we want to find out what happens when we do an S action on theta, we can work that out in a kind of arrow-centric way just by getting this arrow theta under arrow and doing that after HS. And that composition gives us another arrow, this time coming from hom v comma blank into X, and that's going to correspond to this vertex here, which is the vertex of theta here in this bouquet X. So that's the action lemma. The other important one we need then is the natural lemma. So again, I'll show you a picture to start with because it's easier when you see a picture. So this is really a picture of what's going on with the natural lemma. And the basic idea here is that suppose we have, again, in our category of functions, suppose we have an arrow pi, which goes from this bouquet X to this bouquet Y. Okay, so notice it's mapping the vertices of X to vertices of Y. It's mapping the loops of X to the loops of Y. And let's suppose we have a particular loop theta of X that we're interested in. And we want to know what happens to that under this arrow pi. Well, using the kind of Yoneda idea, we can represent theta here as this arrow theta under arrow from hom e comma blank to X. And then if we want to find the arrow which will correspond to the kind of image of theta under pi, then all we do, according to this kind of action lemma, which I'm about to explain in more detail, is basically we just do pi after theta under arrow. And that composition gives us this red arrow here, which really points towards the thing that theta got sent to under pi. More precisely, it's going to be the kind of arrow from hom e comma blank to Y, which corresponds with what we get if we do the ETH component of the natural transformation pi on theta. Okay, so that's basically what the natural lemma says. Of course, the natural lemma, again, it applies for a sort of general category set to the power of C. We don't necessarily have to be talking about the category of functions. And so more precisely then, what the natural lemma says is this. For an arrow pi from an object X to an object Y in the category set to the power of C, and for an object E of the category C, and for a E-type element theta of X, we have that pi subscript E theta, we have that the natural transformation corresponding to the image of theta under the ETH component of pi is equal to pi after theta under arrow. Okay, so it's basically what I just explained, but in more kind of algebraic and general terms. So how do we prove this? Well, again, we basically just use the kind of way that this Yoneda correspondence works and play around a bit with the algebra, and we get the equality. So it's a similar sort of approach to what we did with the last lemma. We want to show that these two natural transformations are equal. So we'll pick an arbitrary component in this case, we'll look at the Veef components of these natural transformations, and we're going to see how those natural transformations work for a sort of arbitrary member of the source set. In other words, we're going to pick some S in Hom E comma V, and then when we look at the Okay, so our basic approach to proving this is kind of similar to before. We have these two natural transformations. We want to show that they're equal. So we're just going to pick an arbitrary sort of component of these natural transformations. In this case, we're going to look at the Veef component of these. And so we're going to have basically two functions to compare. And then we're just going to show that those two functions work the same way on an arbitrary kind of element of their source set. In our case, we're going to look at a sort of arbitrary element S of Hom E comma V, and we're going to show that doing the V component of this natural transformation on S gives us the same result as doing the V component of this natural transformation on S. So effectively, we're going to be showing that this purple arrow equals this orange arrow because they'll work the same way. These functions will work the same way on an arbitrary element S of their source set. So let's do it then. So firstly, let's consider what happens when we do this orange arrow on S. So we want to think about pi after theta under arrow. We will think about what happens when we get the V component of that and apply that function to S. So this is just a sort of composition of natural transformations. And so we can just sort of compose the V components. So we can rewrite this as the V component of pi after the V component of theta under arrow operating on S. So that's just going to be pi subscript V after x of S of theta. This is applying the kind of definition really of theta under arrow that we've already seen. So we've got the result of doing the orange arrow on S. Now we just have to compute Okay, so basically then, to prove this natural lemma, what we want to do is to show that these two natural transformations here are equal. So to do this, we're just going to look at a sort of arbitrary component of these natural transformations. We'll look at the V component of these natural transformations, and then we're just going to be comparing two functions. And once again, if we can just show that those two functions work the same way for an arbitrary element of their source set, then we'll be done. So we look at the V component of these natural transformations. These correspond to these purple and orange arrows respectively. And we just want to show that these two arrows, these two functions here, are going to operate the same way if we apply them to an arbitrary element S of their source set, which is Hom E comma V. Okay, so basically we just want to show that doing this purple arrow on S gives us the same result as doing this orange arrow on S. So all we really have to do is compute what happens to S under these two different kinds of arrows and show that the results are the same. So firstly, let's think about what happens when we apply this purple arrow to S. So in other words, we want to compute pi after theta under. So in other words, we want to compute pi after theta under arrow. So in other words, we want to do the V component of pi after theta under arrow on S. Okay, so what is this? Well, this is just a composition of natural transformations, and we're looking at the V component of it, so we can rewrite this as pi subscript V after theta under arrow subscript V applied to S. And then for this bit on the right, we can just look back at our definition of theta under arrow, and we notice that we can rewrite that. So basically we can rewrite theta. So basically we can rewrite what, so basically we know that doing the V component of theta under arrow on S just gives us x of S of theta. Okay, so we can rewrite this whole thing as just pi subscript v after x of s of theta. So that's okay. We've computed what happens to s under this purple arrow, and this is the result here. So all we have to do now is see what happens to s under the orange arrow. So let's do that. So this time, we're getting this natural transformation here, which we're calling pi subscript e of theta under arrow. Okay, and we want to take the VEEF component of that and apply that to this element s of Hom e comma v. So how do we do that? Well, basically, we have this element pi subscript e of theta, but if you think about it, since pi subscript e is really this function from capital X of e to y of e, we're going to have that pi subscript e of theta is actually going to be an element of y of e. Okay. And so we have this element here of y of e, and we want to really find the kind of arrow from Hom e comma blank into y, which is kind of like the arrow that corresponds to this element under the kind of Yoneda correspondence. So we can do that. So here's a sort of, this is basically what I wrote down before, the essence of this kind of Yoneda correspondence, how we can find an arrow corresponding to an E-type element. But this is the idea sort of when we're working with an object Y instead of an object X. So it's nothing special. It's just the same thing we've already seen, just with a Y in front instead of an X. So in this case here, I'm saying when we have an element theta dash of Y of E, the natural transformation corresponding to that, well, it's going to be theta dash under arrow, and the VEEF component of that is going to be such that if it's operating on an element S of Hom e comma v, then the result's going to be y of s of theta dash. Okay, so we can just apply this result directly, because in our case, yeah, we've got this s from Hom e comma v, and if we just set theta dash to equal pi subscript e of theta, then we can just substitute into this formula, and we find that doing the VEEF component of pi subscript e of theta under arrow on s is just going to give us y of s of theta dash, where theta dash is pi subscript e of theta. So in other words, it's just going to give us y of s of pi subscript e of theta. Okay, so that's how we get this equality here. And now finally, I claim that these two things are equal. Okay, so we've already computed that the purple arrow here sends s to this thing up here, pi subscript v x of s of theta, and we've just computed that the orange arrow sends s to this thing here, y of s of pi subscript e of theta. But it turns out that these two things are equal. Why? Well, this happens because of the naturality of pi, because pi is a natural transformation. What do I mean? Well, I mean that because pi here, I said it was a natural transformation from this functor x to this functor y, that means this square has to commute. Okay, now all the arrows involved in this square are just functions, and so if we just think about how these functions map, starting with an arbitrary element theta of x of e, then we end up getting that pi subscript v after x of s of theta which is what we get by going along the left and the bottom of this square, is equal to y of s of pi subscript e of theta, which is what we get by going along the top and the right of this naturality square. And look, this equality here is exactly saying that these two things are indeed equal. Okay, so that's basically proved the result, because we've basically shown that doing this purple arrow on S gives the same result as doing this orange arrow on S, and this argument works for any element S of Hom E, V, and it works for any V. So that means that these two natural transformations are equal, and we've proved this natural lemma. So that's really the hard work done as far as, understanding the kind of deep mechanics of the Yoneda lemma, at least as deeply as we're going to need them. Now we can really apply them to learn lots of interesting stuff. Just before I move on, let's just have another quick glance at how this kind of natural lemma is working in our category of functions here. And I'll just say it again. Basically, the idea is that if we have an E-type element theta of x, then that's going to correspond to this arrow theta under arrow from Hom E, blank to x. And then if we want to know what happens to theta when we apply this map pi from x to y, we can do that in an arrow-centric way. So basically the result where theta got sent, element-wise, we'd just call that pi subscript e of theta, but our natural lemma tells us that that kind of element of y just corresponds to the thing we get by just doing pi after theta underlined. Okay, so it's really very simple to figure out what happens to things, what happens to sort of bits of objects when we apply a map pi from x to y. All we do is just do that map after the kind of arrow that represents the bit of the object of x that we started with. Okay, so we have this arrow theta under arrow, which is representing theta, and if we just do pi after theta under arrow, that composition is kind of representing what happened to theta when we applied pi. Okay, so let's now go back again to talk about the general case, and we're going to see lots of very interesting kind of consequences of these results we've established about the Yoneda lemma. So basically, this next result is sort of obvious, but it's nice to spell it out because it's very powerful. The idea is that we've already really thought about what these objects in set to the power of c look like. From an element-centric point of view, an object of set to the power of c, it's basically a kind of set of E-type elements for every object E of C, together with a sort of function from x of E to x of V for every arrow S from E to V in the category C. Okay, so it's this kind of structured set, sort of like a database or something. We have all these sets and all these functions from one set to another, and that whole structure basically would correspond to a single object of set to the power of c. I mean, in the case of this category of functions, these structures are pretty simple, right? We just have two sets and a single kind of function x of s that goes from one to the other. But, you know, if C is a more complicated kind of category, then the objects in set to the power of C are sort of more complicated structures involving lots of sets and lots of functions between them, okay? But basically, with all this talk of the Yoneda lemma, we've been arguing that we can think about these kind of E-type elements of an object x in set to the power of c. So we can think of these kind of E-type elements like kind of theta in x of e. We can think of those in terms of arrows. And that's great because basically we already know that we already sort of know that understanding And that's great because we already really know that understanding about what the different types of E-type elements are in an object for the different E, and understanding how they're mapped under these different actions, these different S actions, is really enough to understand what an object is. It's a kind of generalization of the scenario we have in the category of sets, right? If you have an object in the category of sets, and you want to really understand it fully, all you really need to know is what the elements are in the set. And in this case of an object in set to the power of c, it's kind of similar. It's just that you don't just need to know, it's a sort of more complicated version of that answer. We just need to know about not just the sort of, there aren't just elements to an object in set to the power of c, there are elements of different types, and we need to know about all of them and how they play together. And then we understand the kind of essence of an object in set to the power of c. And also, another result we have in the category of sets is, of course, this idea of when two functions are equal. Okay, so, and also another thing which is closely related is this question of when two arrows are equal. And this is very important, okay? Category theory is very heavily focused on arrows, and one of the main things we want to know is when are two arrows going to be the same, okay? So in the category of sets, this is very easy to answer. In that case, the arrows are just functions, and two such arrows are going to be equal when those kind of functions just work the same way on any kind of element, any kind of point of the source set, okay? Now, the case in set to the power of c is sort of similar, and we've already really been exploiting this because I've just been showing you that different kinds of natural transformations are equal. And the way I've been doing it is I've been saying, well, if we look at an arbitrary component of these natural transformations, that's going to be a function. If we look at an arbitrary kind of input to that function, and it gives the same outputs in both cases, that means these two arrows are equal, okay? So we already know that, and that's kind of obvious from our kind of element-centric intuition. I mean, an arrow in set to the power of c is just a natural transformation. It's just a load of it just has a load of components, each of which are functions, and we can prove that, those functions are working in similar ways by thinking about how they work element-wise, how they work on sort of arbitrary elements. So we know that, but now we can sort of put that understanding into the language of arrows, okay? Because we don't have to think about the actual elements of x of e. We don't have to think about theta in x of e anymore. We could instead, of course, now we know about the Yoneda lemma, we can instead think about the kind of arrow corresponding to that, which is going to be this arrow from Hom e comma blank to x that we call theta under arrow. And that's great because we get this nice sort of simple result, which I call the equal arrows theorem. And it basically tells us in a very kind of succinct way this criteria for when a pair of parallel arrows, alpha and beta, from x to y are going to be equal. Okay, so suppose in the category set to the power of c, we have an arrow alpha from x to y and an arrow beta from x to y. Well, this theorem tells us that we're going to have alpha equals beta if and only if alpha after theta under arrow equals beta after theta under arrow for every element theta in x of e, for every object e of c. Or we could equivalently say, if this equation holds for every arrow theta under arrow from Hom e comma blank to x for every object e. Okay, so this kind of basically here just gives us a nice kind of arrow-centric way of testing when two arrows alpha and beta from x to y are actually going to be equal. So we can prove this then. Firstly, it's sort of obvious that if alpha equals beta, then this statement in the orange kind of bubble holds. Because of course, if alpha and beta are the same arrow, then they're going to do the same stuff. So this statement in orange is going to hold. But we really want to show the converse. Okay, so let's suppose that alpha after theta under arrow equals beta after theta under arrow for every element theta of x of e for every object e of c. And now we get the result pretty quickly. So we just use the kind of natural lemma that we've just proved, and that says that we can write alpha after theta under arrow as alpha subscript e of theta, all under arrowed. And similarly, we can write beta after theta under arrow as the kind of natural transformation corresponding to beta subscript e of theta. And so, of course, these things in black on the left and right are going to be equal to each other. And we've just sort of argued that this holds for any element theta of x of e. And so that means, of course, that the eth component of alpha has to equal the eth component of beta. And this also holds for arbitrary e, which means that alpha and beta are indeed the same natural transformation. Okay, so we've now just proved that this statement in the orange bubble here implies that alpha equals beta. And of course, as I've said, proving the converse is easy. If alpha and beta are the same, of course, they act the same way as is described in this orange kind of bubble here. So that's our equal arrows theorem done.